Slides here. We were talking about overview of Java. Just to remind us that we were talking about some of the features of Java that are important for you to understand thoroughly. One of those was the difference between characters and strings, and also illustrated on this slide and the next, the notion of the primitive objects like chars and ints, and the corresponding real objects. Sorry, the primitives, I shouldn't call them primitive objects, the primitives like chars and ints, and the corresponding real objects like character with a capital C and integer with a capital I. Okay, so those were illustrated here. Then we talked about arrays and collections, and we said, well, don't use arrays unless you really, really need the efficiency and you are really sure that the fixed size that you pick when you declare the array is a reasonable fixed size, because fixed size gives you inflexibility. And instead of using arrays, think about collection classes. There's a number of them available, such as a class called ArrayList or a class called Vector. And if you use those classes, then you have these things called iterators, which you can use to nicely iterate through the classes, getting one element at a time. Then we talked about casting and the notion that if you know that a variable has an object in it that is some subclass of the type of that class, then you can use the casting operator that looks like this with a bracket around the class name to say, yeah, treat the result of the subsequent expression as if it were, in this case, a string. And that is useful for situations where, for example, we use a vector which can take any object in it, and we want to start processing the elements as strings. And there are many other situations where you need to do this. It does make your algorithms in code a little bit more complicated to use casting. They look more complicated, slightly harder to read, but it's sometimes essential. If you can do something nicely without using casting, it's probably better, but casting is available and is an important feature. Then there is the notion of exceptions. Exceptions are, well, things go wrong. Well, sometimes the things that go wrong are like dividing by zero, which are arithmetic things, or a socket has timed out in a communication channel. We'll talk about that. We'll see lots of that kind of stuff. Okay, and those are system exceptions. And you have to be able, whenever you use any of the methods of those classes, you have to prepare for those exceptions to happen by using a try-catch block. In addition to that, you can write your own exceptions, and you did see an example in this postal code lab where there was a postal code exception. That postal code lab was designed to get you exposed to some of the things in Java that you might have been a bit rusty on, and one of those was this noticing exceptions and the fact that you can write your own. Okay. We're going to see a lot more exceptions in coming labs, a lot more of all of this stuff, in fact. And then that brings us to the notion of interfaces. Okay, so an interface acts very much like a class, except that it does not have any implemented methods or you can't instantiate it. So it's like an abstract class. Okay, so the key thing is it basically serves as a collection of abstract operations that must be implemented in any of the implementing classes. The implementing classes act a bit like subclasses. In fact, for all intents and purposes, the implementing classes act as subclasses, except that you can have a class implement multiple interfaces, whereas it can only have one superclass. And that gives interfaces quite a bit of power. Okay? And so you'll be exposed to interfaces in this lab, or you have been, and you'll be exposed to them a lot more as time goes on. Some people are of the opinion that you should use interfaces much more widely than they are typically used in software engineering. It's an innovation that Java brought in, and in fact, some people say, well, instead of using a superclass, consider using an interface. The drawback to interfaces is because you can't put concrete methods in there, you don't get that reuse of code that inherits. Okay? So sometimes superclasses are a better idea than interfaces. Okay? Any questions at this point before we push on to a few other details of Java? Yeah?
What's the difference between an abstract class and an interface?
The difference between an abstract class and an interface is that an interface, you can, when you declare a class, you can say it implements many interfaces, but only one superclass. That's the first thing. The second thing is that an abstract class can have concrete methods, but an interface cannot. Okay, so an abstract class, the key about it is it can't be instantiated. An interface goes beyond that. Not only can't it be instantiated, but it also can't have any concrete methods either. Okay? And so you can use interfaces all over the place. Typical interfaces declare one or maybe two operations. And what that allows you to do is it allows you to scatter around, implement classes all over the system that implement this interface, to do simple things like be able to draw, or be able to print, or be able to be compared, or various kinds of things. And you can declare variables whose type is an interface, as long as all you want to do on that variable is the operations declared for that interface. Okay? Somebody else had a question here? Yeah.
Something about something implementing many interfaces or something?
Yeah, a class can implement any number of interfaces. No problem. That's you know, you don't usually see more than one or two, but you can certainly have a whole list of interfaces that you implement. But you can only be a subclass of one superclass. Any other questions? All right. The next major concept in Java that we want to make sure you understand is the notion of packages. Okay, a package is essentially a grouping of classes where these classes logically form some kind of functional subsystem. Okay, a set of classes that work together to do something together. Some of the internals of that subsystem are exposed outside of the subsystem. Okay, but other parts are not. Okay, and we'll talk about that in a few minutes when we talk about access control. Generally speaking, in fact, as a rule, the way you do it is you put all of the classes that belong to a package in a particular directory, particular folder, whose name equals the package name. And then in each class in that package, you also say that it is in that package. So you say package and the name of the package as well. Okay, that just backs it up and is a check for consistency. Okay, classes in different packages can have the same name because when you refer to a class, you can refer to it using a path. So, for example, I have a class, a package accounts. Inside that package can be several classes designated here by the asterisk. And inside the package accounts, I have the package banking. Inside the banking, I have the package finance. And in fact, the convention is that I should then precede this by the inverted name of my domain name. So uottawa.ca would then be, would the package, the whole path should start by ca.uottawa, or then .site, and then whatever my program is. Okay, so that's the convention for packages. And the idea is that if I have a class that wants to use the facilities that are found in some other subsystem, some other package, I then use one of these import clauses to say, I want to be able to access those classes. And if I don't do this, then the compiler will complain. Okay, say, hey, I can't find those classes. Okay? Any questions about that? Some of the issues to do with packages are a bit subtle, and sometimes compilers work subtly differently on what you're allowed to do and where you're allowed to be and stuff like that. I found the rules are not clear, but all the rules on this slide are just straightforward. Yeah. Yeah, sorry, yeah.
So the only way you'd ever be able to use a package is if you first imported it? So you have to import it, it's like...
Right. That is the standard way. There are compilers, not all compilers are as strict as others. Some compilers see stuff, others don't. But you should use an import clause if you want to use stuff from another package, okay? And the asterisk says I want to use all the classes. I can say a specific class if I want. You don't want to overuse import, though, because if I have too many import clauses, that means that if I ever find that there's too the class is in two different packages that have the same name, my system will, you know, in some situations will get confused, okay? So you should try and only import the classes that you actually need. Yeah?
Are we going to learn how to make packages?
Well, making packages is as simple as making a directory. But you're going to be working extensively with packages and sub-packages, and so you'll see a lot about how it's done in the coming labs. Yeah?
Do you recommend that we put the classes in a package and then we put the main class alone?
He says, do I recommend that you put the classes in a package and then the class, the sort of primary class that starts the system alone? And the answer to that is a very important answer. And I'm going to rephrase it a bit differently. What we're going to teach you, and it's coming up very soon, is that you separate the user interface class, and the main class typically is a user interface class, from the classes that perform the function of the system in separate packages. And so you'll see a lot of examples of how that's done. There are several different strategies, but the answer basically to your question is yes. The class that starts the system is typically outside. Yeah. Okay, let's move on. Access control. 3 keywords, public, protected, and private. If you come from a C++ background, the protected keyword is different from the way it works in C++. You should be aware of that. And the defaults are different. Public means, if I declare a method or an instance variable to be public, it means that instances of any class, code in instances of any class, can access this. Okay? If I say protected as the keyword, when I declare a method or a variable, that means that only code in the package can access, or subclasses, even if they're outside the package. If I don't use any keyword, and I just declare a method or declare a variable, that means only code in the package can access. So that's actually slightly tighter control than the protected keyword. And finally, private means only code in this class, okay, can access. But don't think that inheritance doesn't occur. Inheritance still occurs. It just means that the new code written in subclasses cannot access the inherited stuff. Only the old code that's inherited can access it. Yeah?
Can you illustrate how protected the inheritance package?
Can I illustrate how protected does what?
How it does the package, because subclasses also package, how can you access a variable that is protected?
You access a class, a variable in a class that's protected, or blank for that matter, by simply, you have a variable that's of some type of a class that's in the package or a subclass, and you say dot followed by a method, and you can call the method that is in a class that is somewhere else. Right? You can call the method. That's the key. Right? Or I can access the variable by saying, you know, some class in my package dot x, if x is a variable. Okay. General rule, general principle here. Make things blank, package access, tend towards that. Make things private, especially for variables. Variables, it's a good idea to make them private where possible, or blank, so package only access. But we'll talk more about this as the course goes on. You don't want to make things too public, because that means that your code is exposed to the world, to all the other developers of your system, and they'll start calling and accessing inside your system, and you don't know when they're accessing inside your system, and therefore they might do things that you don't expect them to do, or they might be using it extensively and then start complaining when you make changes. So you like to restrict people to only be able to call a few methods that you trust that won't change, and so everything else inside your system, you know, you have total control of. You can change it as much as you want, because only a few things are public. Okay? That is the general principle that we're going to try and adhere to. And variables need to be more private than the methods. You might expose some methods outside your package, but you, generally speaking, ought not to expose variables outside your package. They should definitely, if somebody wants to access a variable outside your package, they should call a method to get the value. Okay? Which means you can then change the definition of that method or change the definition of that variable as a designer of the package without having to worry about who uses it and what they do with it. Yeah.
By making a method public, you're not allowing people to change it just to use it.
Yes, by making a method public, you're allowing other code that other designers write to call that method. Okay? Whether or not they're allowed to change the method is totally independent. That depends on what's called your configuration management system, which is whether they can edit the file or not. That's another issue entirely. Okay?
Exactly. So then why not make it public?
You don't make it public because, generally speaking, in large software systems with multiple developers, so that when you want to make a change, you don't have to go and say, well, I need to make this change. There's a bug. I've got to make a change. I've got to add an argument to my method, for example. You've got to change your code. You've got to change your code. You've got to change your code because you're calling all of my methods. Okay? Whereas if most of them were blank or private, I know for sure that I can make changes to those because I know that nobody else is going to be calling them. It's a fundamental principle of software engineering that's become entrenched and well understood as best practice in the last decade or so. Yeah?
But at the same time, if I've made a method that converts, say, Canadian currency to US currency, then why not make it public?
Okay, you make things public that you want to make public. Okay, things which are useful to others, you make public. But you don't make everything public. You make public just a set of things. And that set of things that you make public is called the API, the Application Programming Interface. You've heard of Windows API? Okay, well, an API is a set of methods that can be called by the outside world. You publish those, you say, feel free to call those. But everything else that does the detailed functions inside is kept protected or private so that you can fiddle with it and make all kinds of changes without having to worry about other people having to be affected. Okay?
One question.
Mm-hmm.
How about the private being for the inheritance? What do you mean?
Private simply means code written in any other class. Code written in any other class cannot access or cannot make calls to the private methods or cannot access private variables. But it has nothing to do with inheritance. A lot of people make the mistake that it does. If I have a private method in a class, that private method will inherit to the subclass. It will be there. It can be called in the subclass, but in instances of the subclass, but only by methods that are also inherited. Okay? I'm not going to go over that again. Think about what I said, and it'll sink in. Okay? It's also in the book. You can read the relevant section over and over again at your heart's content till you figure it out. And if you still don't get it, then email me and I'll try and explain it even further. But that is a point that a lot of people stumble on. It's been an exam question before, and a lot of people have stumbled on that one. Okay, threads and concurrency. The notion of a thread, and this is when we're going to get into threads in a lot of detail into chapter 3, which we'll move into very shortly, is it's a path of control like a program. It works like a program, except that you can have multiple threads executing in parallel, concurrently, at the same time, making your system work as a whole. Okay? The classic example of a thread that is visible to people is a thread that, for example, in a spreadsheet application, let's say Microsoft Excel. Okay? If you're using the user interface of Microsoft Excel and editing the cells, okay, at the same time, in the background, there is a thread that is calculating and updating those cells. And on a slow computer, or if you have a really massive spreadsheet, the execution will lag behind. Execution might take seconds, or many seconds sometimes, to calculate all the changes to all the cells when you make a change to one cell. Okay? I assume you all know how to use spreadsheets, so I assume that this is, you understand the concept there. But nevertheless, the system doesn't hang and wait. When I make a change to a cell, I can immediately make a change to another cell. And what's going on is behind the scenes, there is another, effectively a program, we call it a thread, that is doing the computation to update any affected cells. So in parallel, I have one program that controls the user interface, and a second program that controls the computation. And they're both running in parallel, so you don't have to wait for one to finish before you start the other. They're both going on in parallel. And that gives threads a lot of power. It means that you don't have to wait for things. You can get on with your work even while other work is still going on. Now, if you're working on a computer which only has one CPU, in fact, only one thread can execute at a time, but they alternate their work so frequently, like typically every few milliseconds, that you don't see. And so from the end user's perspective, these things are executing in parallel, when they're really doing little bit, little bit, little bit, little bit, little bit, like that. Okay. So that's what's really happening. But on a multiprocessing computer, with an appropriate Java virtual machine, all these threads can execute with real concurrency. And actually, multiple CPUs can be used to do multiple things at once. In this course, we're going to be seeing a lot of use of threads and how important they are, and we'll be getting to that very soon. There's a number of ways of creating threads. You will be there are exercises in the book which you'll be doing in the lab, which will get you used to the use of threads, starting in the next lab cycle. Okay, Lab B. But this is sort of to give you a little bit of an introduction. First of all, there's an interface called Runnable. Runnable is an interface which says any class that implements it must implement a number of methods. But the main one that we're interested in, I guess Runnable only has the one, is called Run. So if I want to create a thread, I create a class that implements Runnable and has a run method in it. This run method acts like the main program for the thread. You said the thread is like a program, right? Well, like any program, it's got a main program, except that in a thread, it's called run. Okay, so when run starts, the thing executes. When run ends, the thread quits. Straightforward concept. If we want the thread to go on and on and on, we have to either make it do a hell of a lot of work, or else we make it go around in a loop, doing stuff over and over again. So the classic thread that, say, waits for user interface, user input says, you know, wait for user input in a loop. When it does user input, it processes it, and then it goes back to the loop again and waits for user input again. And it keeps on doing that until some kind of mechanism kills the thread by saying we don't have any more user input available. And then the thread runs to its end. The run method terminates. Okay? So just think of the run method as a main program. And you're going to have multiple ones of these in multi-threaded programs. Okay? So, you know, in order to start up a thread, you create an instance of this class, and then you invoke the start operation, and you'll see the details of that. I'm not going to get into the details right here. You'll see the details in the lab. But there is a start operation that you invoke, which will in turn call the run method of your thread. Okay? All I want to do now is give you the concept of how threads work in Java. Java has a very nice mechanism for threads. There are some subtleties and there are some tricky bits. And one of the things you'll be doing in the lab when we look at this system, the Object Client Server framework, is you'll be studying the code of that framework in great detail to really learn how threads work. You'll also learn how concurrency works and how things interact with each other and how inter-process communication works and things like that. The final thing I want to talk about, and this is now moving beyond the scope of Java, is when you're doing programming in this course, follow programming style guidelines. I'm not going to go over these in detail. I'm just going to highlight the key ones. Okay? The first guideline is, remember that programs are for people to read. So your job is to design a literary document. You're creating something that's formal that computer can understand, but you could do that with code that looked like a hell of a mess. The reason why you have to make the code nice and neat and indented and commented and nicely structured is because human beings, yourself, but other maintainers, will have to read that. So think of it as writing a literary document with nice formatting. Okay? Choose good names. You've been taught this already, but we will penalize you if you use names that are hard to understand, hard to read. We talked about choosing names of classes the other day. Choosing names of variables, choosing names of anything. They've got to be long enough, but not too long. If they're too long, they take too much space and they take a lot of typing. But anywhere between 8 and 18 characters is probably a good range. But if you need a long name, because you have to be descriptive and you have to distinguish between things, you know, don't worry about it. Comment extensively. Somewhere between 25 to 50% of all the code that you write should be comments. That's the guideline. Okay, but don't repeat stuff that's already obvious from the code. So your comments are talking about high-level issues, describing in general what this is doing, and not saying assigning 1 to I. You don't say assign 1 to I. Well, that's obvious. You know, I equals 1. That's obvious. Okay, you don't comment that, but you comment the general purpose of the algorithm, or the general purpose of the class, enough so that somebody can glance at your comment and and pretty well understand what's going to happen. And then what they look for when they want to actually look at the detail of the code is, you know, does it really do what the comment said, and how does it do it in great detail? Be consistent about how you organize the elements of your classes. So declare variables, constructors, then public methods, then private methods. That's what I suggest. It's not an absolute requirement. You know, some people have different standards, but that's what I want. Question?
Yeah, should we comment more than what JavaDoc expects? Or is that still...
No, you should comment more than what JavaDoc expects, because JavaDoc is going to be commenting the interfaces of things, but you're going to be commenting the algorithms. You're going to be commenting the loops and things like that. And JavaDoc doesn't pick that stuff up. Okay? Be consistent regarding the layout. There are a number of different styles of layout. If you're editing a system which has a certain style of layout, for example, how the curly brackets line up, follow that standard, so that you don't have a mix of a mismatch of different styles in the same system. So you'll see how it's done in this book. 50% of the world believes in lining up like this, and 50% of the world believes in lining up like this. Okay? We did a survey of books on Java. Half of them do it that way, half of them do it that way. I do it that way. That's the way I've done it since I first learned C in 1984. I find that it helps to understand where the beginnings and ends are, because they're vertically aligned, but it takes one extra line. Other people believe in doing it this way. Okay? Whatever you do, just follow the convention that's being used in your system already. Okay? Avoid duplication of code. We're going to get back to this, but cloning is taking a chunk of code from some place that's typically like more than a line. Copying one line and editing that one line is fine, but copying a loop or copying a bunch of stuff from one class to another causes problems, because then if there's a bug in the original place, you now got a bug in 2 places. There's people have done studies and they found large systems sometimes have so much cloning that there's a bug in one place and the same bug occurs in 50 other places, because people have copied the same bug throughout the entire system by cloning. Okay? The strategy is, instead of cloning code, you create a method that has that cloned bit of code in it, and you call that method wherever you need it, rather than copying it from place to place. Okay? Cloning, i.e. copying chunks of code, is not reuse. We're going to talk about reuse. Reuse is very important. But reuse is calling a piece of code in multiple places, not copying it into multiple places. Okay? And this is often, you'll go to industry and you'll see lots of cloning. This is another principle that has now been well established, but in the early days wasn't well established, and so people did a lot of it in the past. Make sure you follow object-oriented principles, like the ISA rule that we talked about. Prefer private or closer to private, like blank, as opposed to making everything public. We talked about that a minute ago. And a principle that I mentioned a while ago in response to your question: don't mix the code that does user interface, i.e. reading or writing to the screen, to standard input, standard output. Don't mix that with code that does computations. Okay? You'll notice in the postal code system we had a class that did the I/O. Okay? And a postal test, and a separate set of classes that actually stored postal codes that didn't do I/O to the user. It's okay to do I/O to files and databases to some extent, but I/O to the user, i.e. the user interface, should be separated. And that allows you to change the UI, to make a different one, for example, to make a graphical one. It also allows the class itself, the postal code class and its hierarchy, to be plugged into different applications, to do different things. If you embed user interface stuff in that, you're forcing them to be stuck with that one piece of functionality. Okay? Very important principle. We'll reiterate that through the course. Any questions about these low-level sort of programming issues before we move on? Okay. At the end of each chapter, there is a section called Difficulties and Risks. I didn't talk about the one from Chapter 1, but you can look at that. The one from Chapter 2 says Difficulties and Risks in Object-Oriented Programming. And here are some of the things that, when you're doing software engineering, in this context, you need to think about. One of the principles we'll talk about as when we get later in the course is the principle of risk management. And that is that as you're developing software, you need to be aware of things that can go wrong so you can head them off at the pass. So you can say, okay, that could go wrong, therefore we ought to follow this strategy to guard against it happening or to be prepared if it does happen, etc., etc. Okay, if you're not aware of the risks, you're going to blunder into them. So, one of the risks in object-oriented programming is language evolution and deprecated features. If you started programming in Java in 1995, in the early days, you will have started using a number of things, a number of classes, a number of methods that are not recommended today. For example, the enumeration interface that we talked about. We said you should use iterator today. Well, that's because when they first designed Java, it was nice, but there were some things that were weak about it. Okay? Now we don't recommend doing that. So if you use the enumeration mechanism, that means that your code now has to be changed. And so by using things that might be deprecated or that are deprecated, it might mean that they get dropped from the language later on. It's common in all programming languages, but it's just something to watch out for. Another issue about Java is that it could be less efficient than other languages. So you have to make sure when you make a decision to actually use Java that you're not doing something which is going to require a vast amount of number crunching. If you're going to be computing large mathematical operations that will have to crunch for a long time, doing many billions of operations, then, maybe C++ or C would be a better alternative than Java. Okay? So those are just a few things to think about, and if you sort of have those keep those in mind, that will allow you to avoid the risks, and you'll end up being you'll end up running into fewer problems. Your system will work better, etc., etc., etc. Okay, now we're going to move on now to Chapter 3. Chapter 3 is entitled Basing Software Development on Reusable Technology. So we're primarily going to talk a little bit about reuse in general and a lot about a particular reusable technology that we have developed for this course, for this book, that is the basis of a number of labs and will give you experience not only in reuse and in frameworks and in those general principles, but also in a very specific reusable technology, the technology of multi-threaded client-server communications. So first of all, let's just talk a little bit about some general principles of reuse. Reuse is a fundamental software engineering principle. We want to reuse a number of things. They're listed on this slide too. Reuse of expertise means you learn from people. You learn from your colleagues, you learn from people like me, and you learn from books. That's fine. You learn from standard designs and algorithms that are published and are well understood. So there's standard ways of doing sorting and searching, which you'll learn about in courses on data structures, which many of you are taking now. You're going to reuse libraries of implemented. You see, designs and algorithms are designs. You can implement them multiple different times, the same design. Moving down, getting more concrete, libraries of classes and procedures are implemented code. So in Java, there's tons and tons of implemented code you're going to reuse. Moving down further, you're going to reuse built-in things in languages and operating systems. So you're going to use built-in facilities of the Java language like strings and floating point value primitives and things like that. And you're going to call operating system functions for doing things like file I/O and data communication and stuff like that. Getting even more concrete, you're going to use framework. A framework is a whole set of pieces of system that don't have enough functionality to be called a complete application, but are almost there. And that's the topic coming up, so I'm going to leave that for discussion in a few minutes. You just fill in some details to make an application. And finally, you reuse complete applications, such as Office suites. So you might very well say, I'm going to reuse Microsoft Excel or Microsoft Word, and I'm plugging Microsoft a bit here because that's what I use. You could use Corel WordPerfect as well in the same way, and write macros. So you actually could write software inside a completely reused application. And that way you get all the full power of the word processing or the spreadsheet functionality, and then you automate some functions that take advantage of that functionality. So that's reuse of complete applications. And what we want to strive for in software engineering is to reuse as much as possible and to set up our designs so other people can reuse them as much as possible. Okay? We'll see some of the ways of doing this as we move forward. Reuse, i.e. doing the reuse, and reusability, i.e. setting up our designs for others to reuse, is not easy. It's been a big problem in software engineering for a number of reasons. Okay? One reason is that people say, gee, I am going to develop some code that's going to be really neat and work really well, and I'm going to spend a lot of money and time developing it. You know, why should I make that available to others? Because then they get it for free, or they get it, you know, without all the effort that I went through. Well, you could sell it. Fine, but what if you're working inside a large company, and a lot of software is developed in large companies? You're working in your little group. Okay, your little group gets brownie points for delivering software on time and on budget. You know, some people have the attitude, why should I help the other group over there get brownie points by sort of giving them? You know, typically in companies, there's not a trade, a money exchange. You know, there may be some companies there is, but in many companies, you know, there isn't. And so people say, well, we're just going to keep our code that we design inside our little group, and that's it. And so the other group over there that has to do the same thing implements the same thing all over again. And so do 10 other groups inside your company, and so do 10,000 groups in companies around the world, all implement the same basic functionality, the same classes that do the same kind of thing, same kind of algorithms. Okay? That is the tendency in the industry. There's a tendency to say, well, let's not make it reusable, let's keep control. Okay? There's a tendency for management sometimes to not properly reward reuse and reusability, because they don't see it as a major objective. Their major objective is to deliver the product on time and on budget. And they're going to be shot at, you know, verbally and financially if they don't deliver their project on time and on budget. And putting a bit of effort into reuse and reusability, they might not think it'll pay off. They might be nervous about reusing because, gee, what if the code from the other group over there doesn't work properly? That'll hold us up. If we do it ourselves, you know, we can trust ourselves. That might be misguided, but that's the way it often works. Similarly, you know, if we start making our code available to the other group, they start wanting changes to it, then, you know, that's going to impact us. We're going to have to take time to make those changes for them. So let's not get into that business at all. Okay? That's the negative reactionary approach. The problem with that approach is that it costs big time. In the net scheme of things, everybody will develop the same thing over and over again, and we don't get reuse. So we have to combat this, and it has to be done at a management level, it has to be done at a technical level as well. We have to all work together to try and combat these attitudes. Part of it is designing quality code, designing using engineering principles so people trust your code, and you can trust their code. Part of it is using good configuration management, writing good requirements so you know what the other code does. Part of it is good testing so that you can say, okay, the reusable code is all tested, we all trust each other's code, things like that. Okay? Sometimes reusable software is created in a hurry. And so people who dabble in reuse get burnt. They say, oh, we're going to reuse the code developed by the other group over there. But then they discover that the other group sort of did it in a rush and it's bad, and so then they say, oh, we're never going to do reuse again because we had a bad experience. Well, you know, again, engineering principles should try and override that. There is a vicious cycle that comes about. People don't trust code, therefore it doesn't get reused, and so on, and therefore nobody takes advantage of the big cost savings that could be there. What we have to do is we have to put attention to quality, we have to put attention to investment. Good companies will set aside a certain percentage of their resources in a fund and with a group that will focus on developing reusable code and what's called mining reusable code from projects and doing quality assurance on it, keeping it up to date, putting it in libraries for everybody to use. And that will, in the end, hopefully reduce the company's overall costs, breaking the vicious cycle. In this course, we're going to talk about the reuse at the level of frameworks in a lot of depth. So let's talk about what a framework is. Okay, this is my definition. It's a reusable piece of software, should say piece of software, that implements a generic solution to a generalized problem. Okay, a generic solution. So it's solving a problem in a way that is general and broad. It's not solving the problem in a specific way. The specific details have to be added. Okay? It's providing common facilities, and we're going to see some examples of that in a few minutes. Okay? The idea is, the reason why frameworks work, and the reason why frameworks are a good idea, is that many applications that do similar things, or do different things, tend to have similar designs. So, for example, every university has a slightly different registration mechanism. The course coding is different. The rules about who can register in courses and what the GPAs are and the deadlines and all that kind of stuff changes from university to university. Because each university considers itself its own little fiefdom and has its own little academic senate that makes the rules. And so you can't just take one university registration application, plug it in somewhere else, and it'll work first off. You've got to adapt it. So if you're developing a university registration system that you want to sell to multiple universities, you develop a framework that has most of the generic functionality, and then you go into the individual university and plug in bits and pieces that adapt it to the specific rules and regulations and formats that that university would use. Okay, that's an example of the use of frameworks. In this course, we're going to be saying systems that communicate over a network have a lot of stuff in common. You know, they have to be able to establish communications. They have to be able to listen for messages coming. They have to be able to react to messages that arrive, okay? And that, you know, is common among all these applications. So we're going to work on an already developed framework for communication among processes between clients and servers. Any questions? Okay. A framework is intrinsically incomplete. The things that we have to fill in can be called the slots and the hooks. So we'll talk about those. A slot is something which classes or methods in the framework call, but are missing. So for example, there might be a method that is missing called compute GPA. It's missing because every university does it differently. You can't write a piece of code that will work for every university, compute GPA. It's just missing. So that piece of code is missing. Maybe there is in a superclass, there is an abstract method called compute GPA that returns a numeric value, okay? And there's no implementation in any subclass. So this code cannot work because that code is missing. So when you take this framework and bring it into the University of Ottawa and say, we're going to implement, this framework for our registration system, you've got to write a class that has an implementation of compute GPA that works for the University of Ottawa, using our rules. Okay? So that's called filling in a slot. The slot is missing. In the object-oriented context, it would typically be declared as abstract and not implemented. Then we've got things called hooks. A hook is a piece of code that in the framework is implemented but does nothing. And you can override it to do something if you want, but you don't have to. Okay? So a slot you have to implement, a hook you can implement in order to add extra functionality to your system. Okay? So for example, in the university registration system, it might be that the default display of the grade is equal to the numeric GPA. Well, that only works if you've got a university that, typically they don't do that in North America, but that uses numeric grades, percentages, okay? If you want to, in a North American context, to say, well, the display of the GPA has got to be computed as a letter grade from a numeric value, then you have to override the default and do a computation that says, okay, it's actually a letter value that looks like this. Okay, but you would get a default, and you might say the default either does nothing or does something very straightforward, but you can override it. In general, we say that the most common kind of hook does absolutely nothing. Okay, it would return blank, and you have to create something that does something useful. The final thing that we have in frameworks that we're interested in, aside from the inner detailed workings that are private and we never see, are what are called the services. The services are methods that when we write code outside of the framework that we call. Collectively, these services, this set of methods, are called the Application Program Interface, or the API. Okay? So we have a framework that provides an API that the additional code that you write can call. So, for example, if you're programming in Microsoft Windows, you can call a whole bunch of functions that have to do with windowing and application control in Windows. Again, Microsoft provides you with an API you can program to, as they say. Okay? Questions about these concepts? We will see a lot of this over and over again. We will reinforce the notion of hooks and slots and APIs, but this is the introduction to the terminology. In an object-oriented framework, and these days that's the best way to design frameworks, an API is basically the set of public methods that are outside a package. Anything that can be seen outside a package has to be declared public. We talked about that earlier on, and therefore that becomes the API. So, if you declare too many things public, what you're doing is you're making your API bigger, having more stuff in it. And you only do that if you really want outside users to be able to call these methods. As I said, we talked about this earlier on. The framework as a whole is a collection of classes. Some of the classes are abstract, and you have to create subclasses to fill in slots, for example. And then there are other classes that are concrete and have services provided on them. Frameworks can be used in many different kinds of applications. We talked about university registration. You can have payroll management. Each company has slightly different rules, maybe different union contracts, so payroll works differently. So you can't create a full application easily. You need to create a framework that can be changed and adapted to the needs of the company. Frequent buyer clubs, so airline point systems, air miles, petro points, things like that, They're all frequent buyer clubs of one form or another. Almost every company that does a decent amount of marketing has one these days, or is a member of some larger organization that gives points. But all the rules for all these point systems are a little bit different. All kinds of specials and things like that get get added together. And so you would typically want to take a framework rather than implementing from scratch and add your own rules if you wanted to set one up. Talked about university registration, e-commerce. Hey, you know, whether you're a big company or a small company, these days you probably want a web presence. You probably want to be able to have, you know, the ability for people to do clicking on a product and sticking it in your basket so that you can then purchase it using your credit card. Well, all the code that does all that kind of stuff is basically functionally the same from website to website to website. What you want is you want to be able to buy a framework, and then you want to be able to write your web pages that look nice and distinct to sell your products, but the fundamental stuff that's going to do the work is then a framework that your web pages will call to actually allow for purchasing and all the other things to do with e-commerce, you know, such as arranging for shipment and dealing with billing and host-you accounts and all that kind of jazz. Some of that stuff might be very completely standard and just complete applications, but there will be bits and pieces that are framework-like in the sense that they will have to be adapted to your particular organization's needs. You could also have a framework for controlling microwave ovens, or VCRs for that matter. Okay, often this is called the framework for a product line. So if I'm a company, say Sony or Sanyo, that produces a line of microwave ovens, they're all a little bit different. And over the course of the years, I'm going to come out with new models. But my software is going to be fundamentally the same inside. There'll be little bits of differences where I have to adapt my software for new features that are added in different models of oven. Okay, those new features are basically filling in some slots and hooks and writing a little bit of extra code to do fancy things. The core of the software will be the same from oven to oven to oven, and will be a framework that gets reused over and over again. Questions? Some types of frameworks. We have horizontal ones and vertical ones. Horizontal ones are ones that tend to provide very broad general facilities. In this course, we're going to be talking about a system, the object client server system, for providing inter-process communication and messaging backwards and forwards. That's usable by a wide variety of applications. A vertical framework, sometimes called an application framework, is more complete. It's got more stuff filled in. Okay, I'm showing it as it's fatter, more vertical. Like a microwave oven framework. It has a smaller niche, but does more stuff. Horizontal framework has a broader scope of use, does less stuff. Vertical framework is more specific, does more stuff, has fewer slots and hooks to fill in. Okay, now we're going to now talk about, this is slide 10, we're going to talk about client-server architecture. We're going to get back to the framework for this in a while, but first of all, before we get back to the framework, I want to talk about client-server architecture in general. Very important that you understand the principles. Okay? So a client-server architecture is an example of a distributed architecture. Distributed means that I have multiple computers, typically, that communicate with each other. And the software system is distributed among these multiple computers. Some of these computers, some of the programs on these computers, are acting as what are called servers. So imagine that this desk is acting as the grand server. It provides some functionality that will be used by many other computers all over the room. Okay? It could be an email server that you connect to in order to send and receive email messages. Okay? And all the other computers that do the actual end user work are the clients. Okay? So we have separate programs running on separate pieces of hardware that cooperate to perform the overall task. You've got to have the server, but you've got to have a bunch of clients too. Okay? So a server provides service for other programs that connect to it. Connecting is the key there. They connect. The server could reject. The server could say, I'm not going to let you connect. Okay? You're hostile. You're not, you know, you're trying to hack into me. I'm going to reject your connection. That's one of the things servers can do. But normally they will allow the client to connect because the client's a legitimate client. There might be authentication saying, give me a user ID and password. It's encrypted and we'll check it out. No, bad password, reject. Okay, but if it's a good password, fine. Okay, good. Excellent, okay? Now you're connected, now we're going to send messages backwards and forwards. Some point, the server could say, okay, I had enough of you. Cut you off. Kill the communication. Or the client could say, I'm finished. Kill the communication. Or the network could go down. There's all kinds of ways that the connection can terminate. Sometimes this connection is established and goes on for a long, long time. So like if you're doing FTP, you're communicating by sending a file from a client to an FTP server. That could take a long time if you've got a multi-gigabyte file. On the other hand, if you're doing some kinds of things like downloading a web page, you download the web page and then disconnect. And then connect to another server to get to download another web page. So you've got web servers, and there may be many of them. The client can communicate with multiple different servers, one after the other after the other. And basically the connection lasts as long as you're downloading a page or a piece of a page. Okay, so those are some of the basic notions of client-server architecture. Anybody have any general broad principle problems with understanding what those things are? Okay? These days, you all use clients and servers whether you know it or not. I mean, it's intrinsic in a lot of the software that's used. A lot of software that one time in the past was very much monolithic. We call monolithic software that just runs and never acts as client or server. Okay? Whereas distributed software is becoming the norm. For example, there was a time when computer games were strictly monolithic software. These days, a lot of computer games are client-server oriented. Okay, where you can communicate with other people playing the same game. Or different games, or connect to a server which has a selection of games on it. Lots of possibilities with that today. Even word processors, can act to some extent as clients. They can connect to websites and stuff like that. There's linking going on. I mean, a lot of programs build in all kinds of features and stuff, and some of it is client-oriented kinds of work. Okay? What I want to do is I want to now, on slide 11, talk to you about what happens in a server. This is the generic pattern for what happens when a server runs, okay? So the server's here, and I'm going to go over to the other side of the room, and I'm going to act, when I'm here, I'm the client. So you get a general idea of what's going on between the client and the server, okay? So first of all, the server's going to start running. When the system starts up, you've got to have a server running first off, okay? And the server will, once it's sort of initiated itself, maybe it reads a database to get some data, maybe a password list or whatever, and then it starts waiting for clients. So it waits, and it goes around in a loop, waiting and waiting and waiting. This waiting process is called listening. Okay, so it's listening to clients. Okay, then some client is going to start running. And some client starts up, and the client might do a whole bunch of work, but at some point it says, I need to access that server. Okay? And so it will then try and make a connection. It will send a message that says, I want to connect to the server. Now the server that is sitting here waiting and listening, okay, and we're now down in step 4, accepts the connection if it is willing. It has to be willing, it might reject. Okay? Now the client, if the server rejects, the client might say, oh, I'm going to try again. Sometimes the server's busy, so the client waits a period of time, a few milliseconds, a few seconds, tries again. Depending on the protocol that's established, it might keep trying indefinitely until the server lets it in. Okay? Because some servers say, well, look, I'm going to work with a maximum number of clients at a time, maybe 10 or 100 or 10,000. But once I get to that maximum, I can't accept any more connections because I'll be overloaded. So new clients coming in get blocked off temporarily, or sometimes the server gets totally bogged down, and from everybody's perspective, nobody can connect. But hopefully, with a server that's been designed properly for the expected workload, the client is able to connect. The server accepts the connection. Accept is the key word there. Okay, now the server sitting here is saying, okay, I have a connection to that client. I am now in the state where I'm waiting for messages. Okay, I'm waiting for messages to come from that client. By the way, there is parallelism, there is multi-threading going on here too. Because while this part of me, this thread, is now waiting for messages from that client, the other part of me, the server, is waiting for other clients to connect. So I actually have multiple threads. One thread is always waiting for clients to connect, new clients to connect. And another thread, however many clients there are actually connected, you have one thread for each of them that are waiting on the communication with that client. We'll see that in a few minutes in some diagrams. Okay, at some point in time, our client who has connected successfully says, okay, now I'm ready to send a message. So I will send a message. That message could be a simple sequence of characters or a number, or the message, the actual format of the message depends on the application. At some point in time, the client says, I'm going to send a message to the server. Okay? Usually it's almost immediately after connecting. And then the server says, oh, okay, here comes the message. I understand the client's language. Okay? If I'm an HTTP server, I understand the language HTTP, which means that I communicate with a specific set or protocol of messages that are collectively called HTTP, or Hypertext Transfer Protocol. Okay? One of those languages that I understand is these messages that say, get me a web page. Okay? So as an HTTP server, I get a thing that says, get a certain web page, and then the reply is using a language which my client will understand, typically HTML. I send a bunch of HTML down the tube to the client. Okay, so when a message from the client arrives, the server takes some action and then resumes waiting. Okay, I've done my job. I've sent my HTTP down, my HTML down, and then I'm waiting again, waiting for the client to do something else. Unless the protocol says, as soon as I send my response, I quit. That can happen. Some servers will say, I'm going to kill the connection immediately. But generally speaking, there's a protocol, that says, okay, client says, thank you very much. I have now got the information I want. Successfully, I'm done. And the server says, thank you very much. I'm glad you've got it. Goodbye. And the communication is terminated in a nice, orderly way. On the other hand, what could happen is the client says, there was a network error. Some problems occurred in the communication. Please retransmit. And the server, being a nice, polite server, says, most definitely, here you go again. Okay? That's part of the application protocol. Each application has a different protocol. Some protocols are very polite like that. Other protocols are very rude. And the server might say, tough, bad connection. Die, literal. So we have to design the protocol. We have to design the rules of communication. Okay? Protocol, the word is used in diplomacy, right? How countries negotiate with each other. You can be rude, you can be polite, depending on whether you like the guys in the other country or not. And generally speaking, it's been found that politeness works best in diplomacy, and same thing with computers communicating with each other. They try and be polite, because otherwise, problems occur. Let's just say that. Any questions on this overall mechanism for the server's functionality? Okay, I talked about it in the context of an HTTP server or web server, but the same thing happens whether it's an email server, the same thing happens whether it's an airline reservation server, or whether it's a chat server. We'll be dealing with chat servers primarily in this course, or any other kind of server. Here's a nice little diagram. There's supposed to be some dotted lines from server down and from client 1 down and client 2 down. I'm not quite sure why they don't show up here. It's a resolution problem. This is a diagram that shows the sequence, a possible sequence of what could happen. Each of these things, these boxes at the top, is one of the things that is interacting in this distributed system. One server, two clients, client 1, client 2. This arrow here, listen for connections, says, well, this is what the server does at the beginning. It starts its own process of listening for connections. Client 1 connects. Client 1 then sends a message, and then maybe client 2 connects. The sequence could be interspersed. The sequence is not fixed here. It just happens to be, in this case, client 2 connects. And then, after client 2 connects, the server is ready to send a reply to client 1. And then when client 1 gets the reply, client 1 disconnects. And then, client 2 sends a message. And then immediately client 2 disconnects without waiting for any reply. Maybe it's a different kind of message that doesn't require a reply. Not all messages require a reply. Some messages are just one way, you know? And then finally the server says, I'm done. I've had it with these badly behaved clients that don't ever want to reply. I'm going to quit listening. Okay? So this is called a scenario. And this kind of diagram is actually a piece of UML. It's the UML sequence diagram. And we're going to learn more about sequence diagrams later on in the course. But I think that this diagram should be relatively intuitive to help you understand what goes on. Okay? Now, we don't have to use the client-server architecture when we're developing every kind of system. There are other ways of doing things. For example, we could use a single program on one computer that does everything. We could require people to log into that computer and run locally on that computer when they want to do email work. I mean, that is one style of working things. Rather than have your email client running on your local computer, you have to log in using some terminal protocol, telnet, secure shell or something. That was kind of old-fashioned. I still often use that mechanism myself, but it's a little bit old-fashioned now. You know, most of the email programs now are clearly clients. Another way is to have no communication. I mean, that's one option in some designs. As soon as you allow communication, you open yourself up to security breaches and hacking, right? So some people will specify that in some highly secure kinds of operations, there will be no servers. Okay, because servers immediately mean you have to be very careful about security. Okay? And sometimes you can exchange information with mechanisms that don't rely on client-server communication. I can exchange information by writing to a file and having somebody else read from that file. Or I can exchange information by writing to a database and having somebody else read from that database. Okay? Those are ways of communicating that don't require connecting live over the internet or live over a network. But we're mostly going to be thinking in this course in terms of the client-server architecture. We're going to wrap up today by just talking about the advantages of client-server systems over alternative architectures. I mentioned it can be distributed over multiple machines. That means that you can get the power of many machines working together. Secondly, you have the power of distance. People don't have to be in one place. They can work at any place in the world, or even in any place in the solar system, as long as you're willing to allow for the speed of light to communicate the messages. They're setting up, client-server communications with the next generation of Mars, landers and things like that. It can work. You can have separate people design clients and servers. Okay, so I can design an email client that reads and sends email. That a separate company, totally separate from the company that designs the server, that manages the email postbox mechanisms. Okay, so separation of labor and competitive forces. I can have multiple companies competing to design clients that work with a given server, and that can improve technology and instill price competition. Hopefully, at least. The client and the server are simpler than if you just glom them all together in one big program. Okay? The data is kept doesn't have to be, but can be kept centrally at the server in an environment which is secure and safe from fires and other kinds of disasters. Hopefully we'll have a backup somewhere else, but at least there's one place where the managing goes on. Whereas if I have my data distributed all over the place, I can lose bits and pieces of it accidentally and nobody knows. But sometimes keeping the data all over the place is a good idea, because then I don't have to communicate large chunks of data, and if a piece of data is lost, well, only one piece of data is lost. So there are advantages of centralization, advantages of distribution of data, and I can choose in my design whether I'm going to do one or the other, or both. I can have simultaneous access by many clients, and rather than just have one at a time running as would happen on a monolithic program. And finally, as I mentioned, I can have competition in the marketplace for these things. Okay? So next day we're going to move on. We're going to talk a lot more about different client-server systems and how the client-server system in the lab actually works.